field, magnetic force, torque value. Okay, moving. Okay, so you know pretty well in the previous section regarding that, according to the Henry as well as the Oersted, a current carrying conductor which may produce the magnetic field, vice versa. That means if you apply a magnetic field to the wire, a current is also going to be produced. So how you are going to be observing that? By using the galvanometer, how the deflection which should takes place, you can easily calculate it with respect to, so that in the case of electric field, there we are using the galvanometer. So and that deflection is to be noted. But whenever you coming into the picture of here, magnetic field, there only the deflection which should be observed by using a compass which consists of a needle that is to be here indicating towards the North Pole and South Pole. So this is very, very important with respect to magnetic field and also with respect to electric. Yeah. So here how the action of the magnetic field which should takes place in the case of a moving charge, and what is the magnetic force which is to be acting on a current. And next one is that how to calculate the torque tau value on a current loop. Torque tau equals to mu b. Mu is the permeability, and here force constant, and also b is the magnetic. And also you have to, one thing is that you have to calculate the what is the potential energy which is associated with the current loop in a field. So you, one thing you can remember that here regarding to the capacitance of a capacitor, there only what is the energy stored in a capacitor. So that is, here there is a two plates which is consisting of a capacitor, and where the charge which is to be accumulating on the capacitor plates, and the charge which can resides on the plates of the capacitor, which is in the form of potential energy. There we have been calculated the potential energy U value of CV square. Okay, but here when that is related to the electrostatics capacitance like that. But whenever you are coming into the picture of a magnetic field, there you can be able to find out that here what is the potential energy which is associated with the current, okay, loop in a magnetic field. Okay, here also if you want to calculate it, the potential energy with respect to the magnetic field, that is also which is in the form of U. U is indicating the potential energy. Okay, and also we have to note it down the what is the summary of this. Yeah, let me give you a small introduction about this here. Let us consider that a charge which can alter, that means which is going to be changes with this. When there is an electric field, definitely you have to assume that there is a point charge is there. If it is to be changing here, there should be magnetic field which is linked up with that. Okay, so another charge which is brought near to that here electric field, then feels a force due to that field. Okay, and the So a permanent magnet, a moving charge which can create the magnetic field. There is a printing mistake, and at all the points in the surroundings. Where here the magnetic field value capital B, which can exert the force capital F on any other magnet, or else you have to say that a move which present magnetic field, that is to be representing it as a magnetic field induction. That so how much of the strength of the magnetic field which should be takes place. What is the unit of units standard international SI units of this magnetic field capital B value? Tesla. Okay. Yeah. Now we should focus on the action of the magnetic field on a moving charge. So in this section, we let us consider that how to detect the magnetic induction capital B value which affects on a moving charge. So yeah, there is a link up here between the charge to the field here. That means here when there is a charge, definitely the charge is to be moving. You have to say that it can create the electric field. So if there is an electric field, definitely you have to assume that the current which is to be generating. So there is a current, definitely perpendicularly there is a magnetic field which is to be created. So that's why here a moving charge, if charge is there, field is there, magnetic field is there, current is there, current is there, perpendicularly magnetic field is to be developed. Okay, suppose a positive test charge is there, so which is to be injected and with a certain velocity into a region of the magnetic field, and there is a deflecting force which can be experienced by a charge here, and we assert that a magnetic field which can exist at that point. And also, what is the direction of the capital B? Let the velocity of the unit charge, which is V here, and the deflecting force on it, which is to be found, and at right angles to the capital V value. V is the velocity of the unit charge. And due to the directional change of the velocity, the magnitude and the direction of capital F. F is a force which can be inferred from the experimental observation, and the force F will be maximum when velocity is perpendicular to B value. Why? Why here? Here the vector product V cross B is nothing but a VB sine theta. When theta value is 90 degrees, then you have to measure the velocity of the particle, that is a charge particle, which is maximum. Okay, that is also to be discussed by coming. So let F maxima equals to FVB. Okay, so in this uh, this is the equation 1 which is to be indicating here, and in this the vector definition, capital B may be defined that if a positive charge, that is a test charge q, is fired with a velocity v through a region, and also here a sideways of deflection force capital F, which can be experienced that here by the moving of charge when the electromagnetic induction, that sorry magnetic induction capital B, which is present in the region. So the what is the relation here? F equals to QV cross B. Cross product is there, vector product is there, which is nothing but a cross product is nothing but a QVB sin theta, where theta is the angle between the velocity of the particle V to the magnetic field B produced. Okay, next one. And you can able to see that here vector representation of the force acting on the particle, charged particle, and the velocity as well as the magnetic field. So everywhere there is F equals to here QV cross B, that means perpendicular to each other. That's why here the angle is also going to be denoting 90 degrees here. Let if a charged particle moves with through the region where the electric field capital E and the magnetic field B, which are present. Why? Because of here, when the charge is present, there is a charge, electric field is there. That's why here, if there is an electric field, perpendicularly magnetic field is to be produced along the wire is concerned. So here the resultant force which may be experienced by the moving charge F equals to QE plus QE cross B. What is QE here? Where here there is a point charge Q is there, capital F is there, okay, and F is there, definitely intensity of the electric field is there. What is the relation between the E, F, Q? We have been discussed in the case of electrostatics chapter. What is that relation here? F equals to F, Q, and E values. F equals to QE or E equals to here F by Q. Okay. So here, what is the E value? Intensity of the electric field. So what is the definition of the intensity of the electric field? Which is nothing but the ratio of the magnitude of the force to the charge. The ratio of the magnitude of the force to the charge. F by Q is nothing but a intensity of the electric field. That's why here, if A equals to F by Q or F equals to QE. So when there is a moving charge, a charge is there. Definitely you have to write it down that QE electric field is also to be produced. So that's why here F equals to QE plus here QV cross B. Okay. So this is nothing but a Lorentz force equation. Okay. So please remember this, F equals to QE plus QV cross B. Most of the time, this question is asked as a objective. So while you are going to writing the groups exams or group 1, group 2, group 3, group 4 and SSC Staff Selection Commission, RRB Railway Recruitment Board. Okay. So many times with respect to the physics subject, this question is asked as a short question. That means objective type of question. So what is the Lorentz force equation? Lorentz force equation is nothing but F equals to QE plus QV cross B. Please remember. Next. Magnetic force on a current. Let us consider that a current in a wire may be visualized. How? An assembly of moving charges. Hence, if a current carrying wire is placed in a magnet, a force of Lorentz, which will be act in the wire, and we can easily see that a figure A and also figure B. Okay, so there is a field, magnetic field, capital B. Inside it, a point charge is placed. Due to that, field is also to be generated. How the Lorentz force which is to be takes place. Okay, you can see the figure B also. So that's why here let a wire of length I carrying a current I be placed. So here length is smaller, current is carrying I babu. So print mistake is there, you can correct it. Place it in a magnetic field of strength capital B. So what is the direction of the current density, which is to be denoting here capital J value? Okay, J equals to I by A, the ratio of the current to the area. Okay, and also magnetic field vector capital B, which is taken as to be perpendicular to the each other. So here a current in a wire which can carry out the free electrons, and also here the magnitude of the force on a single such electron which can be given out F equals to QVD B sin theta. So what is that here? The angle theta equals to 90 degrees. Babu. Print mistake. This is not 900 and 10.5. If sine 90, theta is 90, sine 90 is 1. So that's why you can remove sine theta. So only the remaining is QVD B. And also what is V? Drift velocity. J by NQ. J is the current density, N is the number of electrons, and Q is the charge. So F equals to Q J and J by NQ into B, or F prime equals to JB by N. Let the volume of the wire is B into LA. That is not 1A LA. A is the area of cross section, and the total number of electrons in the wire is NaL, small NaL. So substitute here. Okay, F equals to NaL, NLAF, and by doing that and simplifying that equation, F equals to LIB or ILB. I is the current, L is the length of the wire, B is the magnet. Okay, and also here which can write down that here if the wire is right angles to the B here, what is the general form? Ideal cross B. Okay, so cross product. Ideal means by integrating the DL from 0 to L length, integrating DL which can gives only length L, IL cross F equals to IL cross. Next, last topic is torque on a current loop. When you can see that figure here, see the figure. There is a magnetic field, the line of force of field, arrow marks indicating here. Inside a rectangular shape of loop is to be kept inside the magnetic field. అర్థమవుతుందండి? లాంగర్ లెంత్ యారో మార్క్స్ ఏమో క్యాపిటల్ బి అని సూచిస్తున్నాయి. రెక్టాంగులర్ షేప్ ఉన్నదేమో వైర్ అది, దాని ద్వారా ఐని గనక మనం జనరేట్ చేస్తుంటే హౌ ద ఫోర్స్ ఇస్ టు బి ఎక్స్. సో రైట్ సైడ్ ఏమో అప్పర్ డైరెక్షన్ లో ఉంటుంది ఫోర్స్, లెఫ్ట్ సైడ్కి వచ్చినప్పటికి డౌన్వర్డ్స్ లో ఉంటుంది ఫోర్స్. ఓకే, so that is to be calculated and doing the calculation here. Let me say you that when a current loop which is to be placed parallel to the magnetic field and the force which should acts on the loop in such a way that and it tends to rotate the loop, and what is the product of the tangential force and the radial distance at which it acts, which you can call it as a torque or a mechanical moment of the. So the torque has a dimensions and the force times the distance and the experience with respect to the newtons meter. Let us calculate that there the rectangular loop with sides of length L and D which is placed in a magnetic field of uniform flux density. Okay, so here we are to be talking about the flux density phi b. So there is a field is there, magnetic field, the line of force of field is there. So here how many line of force of field which is passing through the unit surface which is normal to this, then you have to say that there is a flux is to be generated phi b value. So the loop can carry a current I. Therefore, as per that, any element dl of loop is df cross ideal cross df equals to ideal cross b. Okay, cross product. Let a plane of the loop which is an angle theta with respect to b and the cross sectional area. What is the tangential force? F equals to F first. Substitute here. So see here 0 to L, not 1, that is L. L indicates the length of the wire. I is the current, B is the magnitude. So IBL cos theta. Okay. So the torque is also to be calculated. LAB cos theta, tau equals to. So according to that, the torque which is proportional to the current in the loop and to the area and to the flux density of the field which the loop is to be situated. And here the product of the length of the wire, the area cross-sectional area, capital A. And it is to be designated that the magnetic moment or magnetic dipole moment of it, which is to be denoting here mu equals to NIA, capital N is the number of time, value tau equals to mu b cos theta, not cos t. Several mistakes are there, you can correct it. Or else tau equals to b sin A, sin alpha, mu b sin alpha. Okay. So alpha is the angle between them. Therefore, tau equals to mu cross b or mu b sin alpha. So what are the questions which is to be giving to you? Okay. See here, what is the force exerted? Force exerted on a current carrying conductor when it is placed in a magnetic field, and also torque on a current. Next, what is the potential energy which is associated with the current loop in a magnet? When a magnetic dipole What do you say? A magnetic dipole which is placed in an external magnet. Then a torque acts. Therefore, here the work done by an external agent will change the orientation of the dipole. The magnetic dipole has a potential energy which is of the orientation of the external, where this energy of the dipole, the magnetic is zero, where mu right angles to it. Right magnetic potential energy in any position that an action. So the magnetic potential energy in any position which can be defined as the work that an external agent must do to turn the dipole from its zero position. Okay? Here the angle is also given out to you, 90 degrees the position if it is to be changing. So what is the potential energy from 0 to alpha? TD alpha. That is equals to TD alpha value NIAB. The T is nothing but tau here. Tau value can already NIAB sin alpha D alpha. There is a print mistake. You can correct it. U equals to mu V integral 0 to alpha sin. By doing that, mu naught is the permeability, V is the magnetic induction. So what is the summary? Magnetic field and magnetic force on a torque which can derive the action of the magnetic field on a moving charge, and magnetic force or a current. So here a current loop which should place it parallel to the magnetic field of the force act on a loop in such a way that it tends to rotate the loop. So see here, what are the model questions given to you? Discuss the action of magnetic field on a moving charge and derive the equation, calculate force on force reacting on a current carrying wire which placed in a magnet. Next one. To derive the equation to calculate the force acting on a current carrying in a magnet wire which is placed in a magnet. Next short question. Derive the equation for a torque on a current loop and what is the potential energy? Just now it U equals to mu naught minus current. So this is the thing you have to remember, you have to practice. Next. Today I will give you the introduction portion of the electromagnetic induction. Tomorrow we are going to be concluding the unit 11 and unit 12. So let me give you the introduction portion of the electromagnetic induction. Okay. So here, once again, we are to be recalling that current carrying Henry, first observed is Henry, 1962, according to the Einstein. Okay. Here, when the current carrying conductor, which may produce the magnet, or else vice versa. If there is a magnetic field is to be applied to that wire, a current is also to be generated. That means a deflection is to be takes place in the galvanometer. If you place the galvanometer besides that wire, okay. So that is the case. So here in this electromagnetic induction, electricity is there, magnetism is also there. So here induction, electromagnetic induction. In this case, we have to discuss about that. Induction means here inductance. Okay, that means a coil should be present. What is a coil? A wire which can be rotated into a number of turns. Okay, Nandi? So most of the people now they are using the induction stove. That means electricity passing through that. The coil is to be heated up, okay, and the heat is to be generated. Temperature to be raised. There you can easily cook the whatever the needy items are there. Okay, now. So like that, here two types of inductions. What is that? Self-inductance as well as the mutual inductance. What is that? Self-inductance and also mutual inductance. So in this here we can talk about the here self and mutual inductance. Self means only one coil is present. One coil is to be considered. Okay. So there, if the current is to be passing through that. Okay. So what is the coefficient of the self-inductance? You have to find out. That is to be denoting here capital L value. So L equals to 5B by I. So magnetic induction is 5B, I is the current. The relation L equals to 5B by I. Okay. So here there is applications you need to explain with respect to the self-induction. What are those? Self-inductance of a solenoid. Please remember, this is a very, very important essay question with respect to the Osmani University, Telangana University, Kakatiya University, whatever to be considered. Derive the definition of the self-induction, and also what is self-inductance, and derive the equation for the self-inductance of a solenoid. What is solenoid? If you consider a cylinder, okay, here the wire is to be here the number of turns of the wire which is to be wounding on that cylindrical form, then you have to say that here that is nothing but a solenoid. Okay. And what about the other one? Toroid is also there. What is toroid? Which is in the form of a ring shape. There also number of turns of the wire which is to be wounding on that, the ring. Where do you observe the toroid? You can easily observe the toroid in the case of a ceiling fan. Okay, there you can easily observe the toroid. So you have to find out that what is self-induction and derive the equation for the self-inductance of a solenoid. Next, what is mutual inductance? Second one. Sorry, what is self-inductance? Derive the equation for self-inductance of a toroid. Okay, please remember. So for this, the self-induction, which is for only one coil. Okay, that is a primary section. Next, mutual. When if you are spoke about the mutual, definitely it needed two coils. One is the primary, another one is the secondary. Okay, when the current which is passing through the primary, there in secondary, there should be a deflection. It should take, or else if there is a deflection is to be takes place in the secondary, or when the current is offered by the secondary and the primary coil, here the field is to be generated. Okay, na? So mutual, that means primary to the secondary. So there also you have to find out that what is the mutual inductance of the coil. Okay, so when you spoke about the mutual inductance, two coils is needed. When you spoke about the self-inductance, only single coil is needed. Okay, application oriented, you have to spoke and you have to derive the equation part for that. Okay, Nandi? So that is unit 11. We will discuss in tomorrow's class. Is what is the self-induction and also mutual induction. What are the applications, and also you have to derive the equation part for each of them. Okay, next one. And unit 12, according to the block 4, electromagnetic induction, you have to find out and you have to derive the equation for the Faraday's laws. Okay, so Faraday's laws, EMF, electromotive force, which is equals to the negative rate of change of magnetic flux minus d phi b by d, and that is the integral form. EMF is always equals to line integral E dot dl, which is equals to minus d phi b by d, and you have to derive that the differential form of the Faraday's curly equals to minus dou b by dou. Okay, that means you have to uh, remember that the flux value which is to be changing with respect to time, d by b by d, and the differential form minus dou b by dou, that is to be discussed. And where the negative sign, especially in the Faraday's law, negative sign only EMF, electromotive force, equals to minus dou b by minus d phi b by dt. That negative sign is which is indicating the Lenz's law. Okay, so that is to be discussed. Yeah. So what we have to discuss in the unit 11, that is here. I will give you the only contents, that is self-induction and mutual inductances. You have to discuss about the what are the objectives of this, and what is the introduction portion, and what is self-induction and mutual induction. The self-inductance, the coefficient of self-inductance is capital L, and the coefficient of the mutual inductance is capital M. And yeah, here you can see here 11.4, calculation of inductance of a solenoid, self-induction of a solenoid, and also summary. I will give you only introduction. Tomorrow's class will conclude. So what is the phenomena of self-inductance, which was discovered by the J. Henry. Okay, he is an American physicist in 1832, and where the magnetic field which can be established by a coil is going to be offering a current. Okay, so the magnetic flux lines which are also linked with the coil itself. That means here the current in the coil which can changes the magnetic flux which is linked with it, and due to the magnetic field. So this phenomena of producing an induced EMF, induced electromotive force EMF in a coil due to the change of magnetic flux, change of magnetic flux d phi b by dt due to the current in the coil, which you can know it as a self-induction. Okay, not induction, print mistake. Therefore, the induced EMF produced, which is known as a self-induced EMF. And also, you have to know about the what is the mutual inductance between the two coils, primary and secondary. Okay, and which is also equal to the induced EMF in any coil when the current is to be passed through that. Okay, that means the neighboring coil changing in it. What is the units for mutual inductance? Also Henry. Why? Because of here the J. Henry is only found that a coil is going to be offering a current and passing through the current. Magnetic induction is to be produced. Okay. So on his name only we are to be calling that the units of the induction is or inductance is a Henry. Okay. Millihenry, mH 10 power minus 3 Henries. Like that. Okay. So we are to be concluding today's class, and we will continue with this by tomorrow's class, and we are to be concluding, and that means here the 11th and 12th unit with respect to DSU. This paper is to be ended by tomorrow's class, and later on by coming classes we go for elective. That is for here we took only 6 classes to complete this paper. Okay, so this is only the counseling classes, not by the lecture classes. From the starting onwards I am going to say. Okay, so we have to conclude itself. Okay, so by tomorrow's class we will discuss with that the remaining portion. Okay? Right, all the best.